Welcome to the second submodule on survey interpretation and basic calculations. This module builds upon the foundations from the first part, introducing more advanced concepts in directional drilling mathematics. The objectives of this module are clear and designed to enhance your technical competency. This module builds upon the foundations from the first part, introducing more advanced concepts in directional drilling mathematics. Here, we will focus on circular functions, curvature calculations, build-up rate formulas, and the effects of survey frequency on wellbore position. Circular functions form the mathematical foundation of directional drilling calculations. A complete circle is 360 degrees, which also relates directly to pi times the diameter, or 2 pi times the radius. Importantly, 1 radian is defined as the angle subtended at the center of a circle when the arc length equals the radius. This means that 360 degrees equals 2 pi radians and 180 degrees equals pi radians. From this, we calculate that 1 radian equals 57.2958 degrees. Remember 57.3 because it is a quick hack to simplify the formulae. This conversion is critical for understanding trigonometric calculations used in well path planning. Many directional drilling formulas, particularly those involving curvature and build-up rates, rely on radian measures for accuracy. Arc length is another key concept in circular functions. The length of an arc is determined by the radius of the circle and the central angle in degrees. Mathematically, the arc length is equal to 2 pi r multiplied by the ratio of the angle over 360 degrees, or more simply, pi r times the angle divided by 180 degrees. For example, if the radius is 15 meters and the angle is 60 degrees, the circumference is 94.2 meters. And the arc length comes to 15.7 meters. This calculation is essential for determining the path length of a curved section of a wellbore. The radius of curvature is a key parameter in directional drilling. It defines how sharply the wellbore curves as a function of build-up rate. In US units, the build-up rate, BUR, is expressed in degrees per 100 feet. While in metric systems it is expressed in degrees per 30 meters. The radius of curvature RC is calculated as 180 times 100 divided by pi times the build-up rate. Now look at the diagram on the right. It is an arc that has an initial starting point which moves through the arc to a point of the first survey. It then continues to a second survey point. Therefore, we have moved through a TVD distance to the first survey point and a further TVD distance to the second survey point. The question is, what is the TVD travelled between survey 1 and survey 2? Using RC, we can determine changes in true vertical depth. TVD 1 equals RC times the sine of the initial inclination, and TVD 2 equals RC times the sine of the final inclination. The change in TVD is the final TVD subtracted by the initial TVD. If we substitute in the formula for RC, we can calculate the TVD change. The radius of curvature method also helps calculate horizontal displacements using the same method. In this case, the diagram represents an arc on a horizontal plane. HD1 equals RC times 1 minus the cosine of the initial inclination, while HD2 is RC times 1 minus the cosine of the final inclination. The difference between them gives delta horizontal displacement, expressed as RC times the cosine of I, 1 minus the cosine of I2. As with the change in TVD, if we substitute in the formula for RC, we can calculate the horizontal displacement. The build-up rate formula is one of the most frequently applied equations in directional drilling. It allows us to determine the inclination change per unit of length drilled. Once we know the BUR, we can calculate the end of build position for the well path. The end of build TVD is equal to the kickoff point TVD plus the delta TVD calculated from curvature equations. On this slide, we are looking at how to determine the end of build in a directional well. The build section begins at the kickoff point, or KOP, which is the depth where deviation starts from vertical. From there, the well follows a curved path defined by the build radius. In this example, we're building angle up to 50 degrees. The curved line represents that smooth build in inclination, and the EOB is the point where the curve stops and transitions into a tangent or hold section. To locate the EOB, we need two key pieces of information: the vertical depth drilled during the build, shown as delta TVD, and the horizontal displacement achieved, shown as delta HD. Inclination projection is a practical tool for landing horizontal or high-angle wells. It enables drillers to calculate the build-up rate, additional measured depth, and displacement required to reach a target inclination at a specified true vertical depth. For example, if a well is drilled at 8,402 feet TVD with 80 degrees inclination, and the target is 90 degrees inclination at 8,412 feet, we can compute the build-up rate as 8.71 degrees per 100 feet. The required additional measured depth is 114.8 feet, and the corresponding horizontal displacement is 114.2 feet. I recommend that you stop the video and review the equations and examples to become familiar with them. Survey frequency is a critical factor in ensuring well bore position accuracy. When surveys are spaced too far apart, the actual well trajectory can deviate from the assumed path, leading to significant positional uncertainty. The sequences of sliding and rotating affect how survey averages represent the true well path. For example, a sequence of slide, then rotate, or rotate, then slide, can distort the true trajectory, while a rotate, slide, rotate pattern provides more accurate representation. Careful planning of survey frequency and pattern ensures that the true wellbore position is known and that errors from averaging do not accumulate. Okay, so question. Often a drilling program will state a maximum dogleg for limitations given because of tortuosity or the need to run delicate equipment such as electrical submersible pumps. If I were a directional driller, and I noticed through continuous inclination readings that I had inadvertently put in a massive dogleg, how could I hide it? I will give you a moment. The easy way to do it is to rotate a bit further and increase the distance between surveys. This would average out a smaller dogleg. Obviously, this would be evident if a gyro were run at the casing point. At this stage, we return to the module objectives to ensure comprehension. You should now be able to define toolface orientation and explain when magnetic toolface and gravity toolface should be applied. You should understand how to interpret service company rig floor displays, read survey sheets accurately, and validate geomagnetic and gravity data. Additionally, you should be comfortable applying circular function principles, calculating radius of curvature, build-up rate, displacement, and inclination projections. These skills give you the capability to analyze, predict, and control well trajectories effectively. Thank you for working through the second submodule on survey interpretation and basic calculations. This ends the complete module. Please progress to the quiz.